Find the area of the shaded region. And so we have the upper bounding curve defined here as the square root of x plus the square root of y equals 1. And our lower bounding curve is the x-axis. And we, of course, know that our x-axis is defined by the curve y equals 0. So the first thing that we need to do is solve our upper bounding curve for y. You could solve for x too if you want, but I think it's going to be the easiest here if we keep everything as y as a continuous function of x. So let's solve for y, and then we'll use that to find the bounds. So we have the square root of x plus the square root of y is equal to 1, and we can subtract the square root of x from both sides, and we have the square root of y minus the square root of x. So then to solve for y, we need to square both sides of the equation, which leaves us with y is equal to, and we have 1 minus the square root of x multiplied by 1 minus the square root of x. And if we FOIL this bad boy out, we are left with something we can integrate. So we FOIL this out, and it leaves us with 1 minus 2 times the square root of x plus the square root of x squared, which is just x. So our upper bounding curve is y is equal to 1 minus 2 times the square root of x plus x. And again, our lower bounding curve is the y-axis. So we want to find, we can certainly see here that the right-hand side bound for x is at 0. But what is this left-hand side bound? So to find the points where these two curves intersect, we need to equate them and then solve for x. So we need to find the bounds. And again, to find said bounds, we're going to equate the curves and solve for x. So here we go. So we have, again, we're equating them because y, of course, equals y, which allows us to say that 1 minus 2 times the square root of x plus x is equal to 0. And we now want to go ahead and solve for x. So it can be easier to keep in mind that this trinomial here came from 1 minus the square root of x squared, which we have is equal to 0. And now we can go ahead and solve for x. Right? We can take the square root of both sides of our equation, which leaves us with 1 minus the square root of x is equal to 0, or 1 is equal to the square root of x. And when we square both sides, we see that x is 1. Woohoo! So therefore, our bounds we have that x is an element of the closed interval from 0 to 1. So we're ready now to go ahead and find the area. So let's just take a moment real quick and go back to our picture. So we know we're looking for the area under this curve here, which we have redefined as y is equal to 1 minus 2 times the square root of x plus x. And this is where x is from 0 to 1. So let's find our area. So the area, A, is equal to the definite integral from 0 to 1 of 1 minus 2 times the square root of x, which we'll rewrite as x to the 1/2, plus x dx. And we're ready to integrate. So this will be equal to x minus 2 multiplied by x to the 3/2, all divided by 3/2, plus x squared divided by 2, and we're going to evaluate this from 0 to 1. And so let's rewrite this first. We have x minus 2 multiplied by the reciprocal of the denominator, which is 2/3, times x to the 3/2. And actually, we'll put this into its radical form here. That's the square root of x cubed plus x squared by 2 from 0 to 1, which leaves us with x minus 4/3 times the the square root of x cubed plus x squared over 2 from 0 to 1. And we're ready to evaluate. So plugging in 1 first, we have 1 minus 4/3 times the square root of 1 plus 1 over 2 minus 0. And we, of course, know that the square root of 1 is going to go to 1. So this leaves us with 1 minus 4/3 plus 1/2. And we need a common denominator here and no decimals. So to get that common denominator, we need to multiply 1 by 1 by 6. We'll multiply 4/3 by 2 over 2. And we'll multiply 1/2 by 3 over 3. And this leaves us with 6 minus 8 plus 3, all divided by 6, for a beautiful final answer of 1/6. So therefore, the area under the curve and above the x-axis is defined as 1/6 square units.